Yay. Yeah, thanks, Jeff. Yeah, so I'm going to talk about a few works with a bunch of amazing co-authors that are sort of generally centered around streaming algorithms for a particular problem called the maximum directed cut problem. Okay. Okay, let's see if I can click. Okay, yeah, I can. Okay, so just for some context, this problem, this max directed cut problem that we're interested in is an example of a much broader class of problems that's very widely studied called a constraint satisfaction problem, or CSP. And for these problems, an instance, which I'll typically denote by psi, is given by a bunch of variables. Usually n is the number of variables. Each variable takes a value over some finite alphabet. And then you have constraints, each of which applies some predicate to subsets of k variables. And yeah, typically I'll use m to denote the number of constraints. And the general goal here relates to the value of an instance, which is the maximum fraction of the constraints that can be satisfied by any assignment of the variables to values or symbols in the alphabet. Yeah, and the general goal is that given a description of an instance, you want to estimate the value of the instance. So you want to estimate the value of the highest assignment. Okay, so the most widely studied example of such a problem is the max cut problem, which is over an alphabet of size 2, and it has arity 2, meaning that each constraint only affects 2 variables. And in particular, when you apply a constraint to a pair of variables, the constraint says that those 2 variables have to get assigned a different value. And it's useful to also think of this as a graph, where each variable becomes a vertex, each constraint becomes an edge, and then the goal is to find a cut, which is like an assignment of the variables to either 0 or 1, which cuts as many edges as possible. And an edge is cut if its 2 endpoints are on a different sides of the cut, have a different assignment. And I'm going to interchangeably refer to like instances and graphs sort of using this correspondence. So there's a quote unquote trivial algorithm for this problem. And it's just trivial because you can get an estimate for the value of a max cut instance without even looking at the instance. In particular, for every max cut instance, you can calculate using linearity of expectation that a random assignment in expectation will cut half the edges, will satisfy half the constraints. So what that means is that every instance has value at least half. So if you're trying to estimate the value of an instance, you can just the instance and output half as your estimate. That's sort of a trivial thing because you're not even looking at the instance at all. And the question is, can you do any better than that? And there's this very famous result of Gomans and Williamson from the 90s where they show that using this semi-definite programming framework, you can get a 0.878 approximation, meaning you can output an assignment whose value is like at least 0.878 times the value of the best possible assignment. And there's really only this algorithm and maybe 1 or other 2 algorithms that are known for this problem that do better than the trivial approximation. So there's also this quote unquote spectral partitioning algorithm of Trevisan about 15 years later. But overall, there are very few sort of known algorithms for these problems, and they're all sort of complicated in some sense, like they require doing some optimization or other things like that. So the question that sort of, in my mind, motivates a lot of the questions that we studied is like, what happens if we are thinking about a model where you can't do things that are as complicated as like solving an SDP? Okay, sorry, let's see. So in particular, we're going to consider a model where the algorithm that's trying to estimate the value of a CSP instance has really small memory, like small relative to the number of variables in the instance, for example, and takes only a single pass over the list of all the constraints and is trying to estimate the value. So it's important to note that in this setting, if the amount of space that you have is much smaller than the number of variables, you can't even hope to remember an entire assignment to the instance. So we're not asking you to output an assignment, we're just asking you to output an estimate of the value of the best assignment. Okay, so yeah, you can visualize, I like visualizing this, like, this is a max cut instance, there's some giant list of constraints. The algorithm starts at the beginning, it has really small memory and only can see 1 constraint at the time. It makes this linear pass over the list of constraints, and at the end has to estimate how many constraints can possibly be satisfied by the best assignment. Okay, so yeah, this is like a very sort of, in some sense, a very restrictive model, and you can't do things like solving the SDP for max cut. Okay, and another thing that's nice about this model is that I said nothing at all about time complexity. So there's no polynomial time assumptions or anything. And sort of this is what's sort of nice about studying streaming algorithms in general from a complexity standpoint, is that you can definitively prove unconditional lower bounds that don't rely on any conjectures about certain problems being hard using techniques from communication and some other areas. Okay. And yeah, so another thing which will sort of recur in the talk is that oftentimes for some of these CSP type problems, you can take some natural algorithm and then which may not be sort of naturally a streaming algorithm and then figure out how to sort of fit it into this framework. But for max cut, you can't do that. Max cut turns out to be really, really hard in this model. So there's this result of Kapralov and Kratchun from 4 years ago, which built on several other results, where they showed that doing any constant better than the trivial approximation requires linear space. And that's a very strong lower bound because it turns out that using like n log n space, you can get arbitrarily good approximations. So again, we make no time restrictions. So what you can do is use the sort of generic fact that, say for max cut, if I have an instance of max cut, I can randomly throw away all but n over epsilon squared of the constraints. And that sort of subsampled instance that I get will preserve the original value up to a 1 minus epsilon factor. And I can calculate the value of this subsampled instance because I don't care about the time at all, just about the sort of space or information that I have to store. So this basically means that max cut is really hard. You can't do any better in sort of a meaningful amount of space. Okay, so if max cut is really hard, the next CSP that people sort of thought about was the max die cut problem, which you can think of as an asymmetric version of max cut. So here we apply still a predicate to two variables, but now the variables are not treated symmetrically. And the constraint says that one variable has to be assigned a 0 and this other variable has to be assigned 1. So you can think of this also in graph language, and I'll use these interchangeably. This would be for a directed graph where each edge has a left and right endpoint, and the cut has a left and right side. And you want to find a cut which cuts as many edges as possible in the sense that each edge, its left endpoint is on the left side of the cut and its right endpoint is on the right side of the cut. Okay, so in this setting, similarly to before, a random assignment will satisfy 1/4 of the constraints and expectation. And the question is, can we do better than 1/4? And what's interesting and exciting about this is that you can actually do better than 1/4. So this means that the model is not like completely sort of meaningless in the sense that it doesn't rule out sort of non-trivial approximations to every CSP. And actually, so my co-author Santoshini Velusamy was, I think, an undergrad visiting CMU 6 years ago when they wrote this paper that showed that you can get a 2/5 approximation in very small space to max die cut. Okay, and building on this work, there was this amazing work 3 years ago, which characterized how good of an approximation you can get in a small amount of space. So they showed that in logarithmic space, you can get constants arbitrarily close to 4/9, and in square root n space, you can't do any better than 4/9 by a constant. And I'm going to talk a little bit about how they prove the algorithmic result later. Okay, so now I just want to tell you about what the sort of result that I want to build towards over the remainder of the talk is that there exists a streaming algorithm which uses slightly more than square root n space and achieves a factor, approximation factor, which is strictly better than 4/9. It's better than 0.483. It's not as good as 0.49, so it's not as good as 1/2, which would be like the best thing that you could hope for. Yeah, so this, and I'm going to talk a little bit more about this later too, but this leaves open sort of basically the space between 0.483 and 0.5 and the amount of space between square root n and n. Okay, so this builds on some other works that firstly simplified the 4/9 approximation algorithm and then showed how to beat 4/9 in some special cases. And actually, I'm mostly going to talk sort of technical stuff about those two things, and then sort of hint at how the algorithm for this sort of general case works. Okay, so the picture that I like to have in mind about this is basically we know results at 3 amounts of space at sort of okay, I'm ignoring log factors. So we know what you can do in logarithmic space, which is the 0. We know what you can do in square root n or square root n polylog n space, and we know what you can do in linear space. So in logarithmic space, you know, there's this trivial approximation where you just output the value of a random assignment, which gets a 0.25. There was this result then that showed you can get 2/5, which is like 0.4. And then there was a result that showed you could get 4/9, which is like 0.44 repeating. And that 4/9 is known to be optimal even in square root n space. We show in sort of the current work that you can beat this 4/9 using square root n polylog n space. And then what we know is that, I guess this is, there's a half approximation bound for max cut, and that sort of immediately implies a half approximation bound for die cut too, because there's a reduction from, I guess, max cut to max die cut, where you would randomly direct each edge. So you can get a half approximation bound for that too. And then we also know you can get arbitrarily good approximations in, adding another log factor. So the space that's sort of left open is between square root n and n and between 0.483 and 0.5. Okay. Yeah, and I want to say a little bit more about why this is interesting also. So again, there was this result from a few years ago that showed that 4/9 is the best you can do in square root n space. And this was subsequently generalized in a sort of very significant way to every finite CSP of every arity, every predicate over every alphabet. And they showed sort of a similar thing. Either you have a log space algorithm or you have a square root n space lower bound. And you can think of this as a sort of analog of this famous dichotomy theorem of Raghavendra for SDPs, but in this model. So this sort of dichotomy theorem that proves lower bounds for all CSPs only works in square root n space. But as I mentioned, there's also linear space lower bounds for max cut. And we also have linear space lower bounds for some other CSPs. And so sort of the question is, to what extent is there a real difference between square root n and n versus is this just some artifact of the proofs? And it turns out when you actually do these proofs, like how people usually prove space lower bounds in streaming models is they design certain communication games and show that they have to use a lot of communication. And it turns out like the most sort of natural ways that you would prove these lower bounds, you would use communication games that have square root n space protocols that are very simple, that just rely on some collision probability sort of thing. So the question is like, if you spend some time sort of studying those communication lower bounds, like, is that an inherent sort of problem in the streaming model, or is it just some artifact of how we know how to prove streaming lower bounds? Okay, and yeah, our work sort of provides the first steps towards answering these questions. And I have strong hope that could be sort of generalized both to other CSPs and maybe to other amounts of space between square root n and n. Yeah, okay. Okay, so now I'm going to forget about everything that I just said and just tell you about a sort of simple, hopefully simple algorithm that gets a 4/9 approximation. And I'm going to think about it not for the max die cut problem, but actually for a more general problem because it's convenient in this setting. And this more general problem is the max 2 and problem, where so max die cut, if you apply it to two constraints or to two variables, the constraint says x and not y. And in max 2 and, we also allow x and y and not x and not y. Just this is convenient to think of it as a sort of super class of problems. Okay. Yeah.
Instead of caring about like satisfying many constraints you can, you care about not falsifying as few constraints as you can.
Yes, I think so. Let me think. So we didn't study that problem in the current work. So this dichotomy theorem actually says some very strong thing. It says that like for any pair of values, like either you can distinguish between instances whose values, at least one thing or at most the other thing. And I think like for die cut, we already know that I think the best you can do is maybe 1 minus epsilon versus 1 minus 2 epsilon at least in less than square root n space. But in more space, like in linear space, I think that is also an interesting question, what the best trade-off would be in sort of the high, I guess I would think of that as like the high value sort of regime or something. Yeah, okay. Yeah, so in this setting, when we want to design an algorithm for the max 2n problem, it turns out to be very convenient to introduce this quantity, which I'm going to call the biasedness of an instance. Okay, so what is this? So for any variable, I'm going to look at what is the sort of positive weight of the variable, which means when it appears in how often it appears in the instance without a negation sign over it, and the negative weight, which is how often it does appear with a negation sign over it. And then the biasness of an instance is just the sort of average magnitude of the difference between these two things. Okay, so this is just some number, but it's sort of useful to interpret it. So if this quantity is 1, then it means that for every variable, either its positive weight or its negative weight is 0. So in other words, for every variable, it either always appears without a negation sign or it always appears with a negation sign. Okay, and that means that you can just greedily assign it to either to whichever thing would satisfy how it's appearing, and that means there's an assignment that satisfies all the constraints. The biasness could also be 0, so this is a number between 0 and 1. And if the biasness is 0, that means that for every variable, it occurs equally often positively and negatively. And that would suggest that no matter what your assignment is, it can't be very good, because let's say you assign a variable to 1, well, it occurred just as often in the instance with a negative sign over it. Okay, so you didn't satisfy any of all those constraints where it had a negative sign over it. Okay, and more generally, you can expect that there should be a positive correlation between the biasness of an instance and the value of an instance. And the reason why this is convenient is that this is sort of a magical sort of observation that was made in this paper of Santoshini and others from 2017, is that this biasness quantity is the L1 norm of a certain vector. So you can think of a vector where it's indexed by variables, and the entry for any variable is the difference between its positive weight and its negative weight. So this is simply like a scaled L1 norm of this vector. And L1 norms of vectors can be measured by small space sketching algorithms, sort of in the streaming settings. This is like a very famous result that we can just use as a black box. So in particular, like to think of this concretely, you have this stream of constraints that's coming. Each constraint will have, 2 literals, and then those literals say, increment or decrement the vector at one coordinate corresponding to one of variables, and increment or decrement the coordinate for another variable. Okay, so anyhow, you can just treat this all as a black box for now. Like we can measure this quantity up to like a arbitrarily good constant factors in the streaming setting, even in logarithmic amount of space. So it's sufficient to get an algorithm to prove like a correlation between the biasness of an instance and the value of an instance. And that's what I'm going to do. Okay, does this make sense as like a general plan? Okay. So this is the theorem that the value of an instance is related sort of to the biasness by these 2 inequalities. And if you like rearrange this theorem, you would get, I think that the value is at least 2/9 of 1 plus the biasness, which is at least 4/9 of the value. So this proves that you can get a 4/9 approximation. Okay. So this analysis is actually sort of you can do in like a very self-contained way. And I like thinking about this in some sense because this is like a million times less complicated than what would be involved in doing the analysis of something like an SDP. And the fact that this analysis is so simple is sort of what morally means that it can be implemented as a small space streaming algorithm, or at least that's how I like to sort of think about it. Okay, so yeah.
The statement you said.
Yes.
You're going to elaborate on that?
Yes, I'm gonna prove the. Oh, sorry, I forgot. No, I just completely forgot. Yeah. So yeah, sorry. A useful fact for the analysis is that if I take an instance and then I pick a variable x, and then I decide to flip x, by which I just mean like you take x, you replace every occurrence of the literal x with not x, and every instance of occurrence of the literal not x with x. Okay, this preserves the biasness because it flips the positive and negative weight of the variable, and there was an absolute value sign in the definition. And it also maintains the value. So it maintains both of these. It also maintains the value. Basically, you can think of this change as like a bijection on the space of all the assignments. And so every assignment will be mapped to a new assignment with the same exact variable just by flipping, same exact value just by flipping that variable. Okay. So yeah. Okay, so take any instance of max 2end. Okay, and I'm going to define some letter P2, P1, P0 to denote the fraction of all the constraints that have either both literals being positive, both literals being negative, or one positive literal and one negative literal. Okay, so I'm going to write, this is an equation, and I'm going to try to explain where it comes from. So the left-hand side of this equation is like this biasness quantity that I defined, except that there's no absolute value signs around the thing that's inside of the sum. So this is like a signed version of that thing. Okay, so you can think of the sum on the left-hand side as sort of summing over constraints instead of over variables, and think about how much does each constraint contribute to the sum. So if you have a constraint which has both literals occurring positively, then you can think of that constraint as incrementing the positive weight of one variable and incrementing the positive weight of another variable. So it's like a net +2 to the left-hand side, and that gets canceled out by the 1/2. So it's like a net +1 to the left-hand side. If you have a variable, if you have a constraint in which both variables are negated, then that will contribute 2 -1s to the sum on the left-hand side. So it will contribute a overall -1 because of the factor half. And if you have constraint which with one positive literal and one negative literal, then it's a wash. There's a +1 and a -1, so it's net 0. So altogether, this thing on the left-hand side is just equal basically to the number of constraints with 2 positive literals minus the number of constraints with 2 negative literals up to whatever the scaling should be. So that is true for every instance. And then I'm just going to write down an inequality, which is like slightly, I don't know, it's the inequality that makes the analysis work. So these three things, these three fractions sum to 1 because every instance either has every constraint, but there's a lot of different levels of things to say. So every constraint either has 2 positive literals, 1 or 0. So these three things sum to 1. And I know that this thing on the left-hand side, if I add the absolute value signs, is the biasness. So if I add, like I want to add this P2 plus P1 plus P0 to the right-hand side and add 1 to the left-hand side. And what I get is that 1 plus the biasness is at least 2P2 plus P1. And also there's equality if every variable is, quote, positively biased, which means that every variable occurs, the positive weight is at least the negative weight. Okay. So this is just some inequality that turns out to be extremely convenient when we want to prove the two inequalities that we were starting with. Okay. So, okay, first I'm going to prove this upper bound that says, yeah.
What you got out of this thing?
Oh, sorry. Yes, this inequality is what's sort of convenient, and I'm going to rewrite it on the next 2 slides. I think it shows up in both. So the inequality that you actually want to prove overall is this inequality that relates the biasness to the value, and then this inequality sort of will show up in both proofs, and the thing is just to relate the right-hand side to the value of the instance. Yeah. So first, I want to show this is basically that if you have a high value instance, then the biasness is also high. That's how I would think about this inequality. You need to prove this in both directions. And here's the proof. So first, I'm going to start with any instance. Okay, it has some optimal assignment. I'm going to look at any variable that's assigned 0 in the optimal assignment. I'm going to flip it. Okay, now I get a new instance which preserved the value and the biasness and has the property that the optimal assignment is the all ones assignment. Okay, and it suffices to only consider this instance. Okay, so the value of this instance is the only constraints which are satisfied in this instance in the optimal assignment are the constraints where both literals are positive. Okay, because if I plug in the all ones assignment, the only constraints that will be satisfied are the constraints where both literals are positive. And then from the previous slide, we wrote this inequality. Okay, now you can put these two things together, and this P1, which is the fraction of constraints with 1 positive and 1 negative literal, is a non-negative number. So you can just get rid of it. And then you get just 2P2, which is twice the value. And this is the inequality that you wanted to prove. Okay, so once you, I guess like the point of this is just that once you wrote this inequality, then the thing that you wanted to do was sort of some sort of simple manipulation. Okay. And then on the other hand, and this is actually where we simplify the original analysis somewhat, you want to prove this lower bound that says that if the biasness is high, then the value is also high. Okay, so now I'm going to start with an instance and I'm going to flip it in a different way. I'm going to flip it so that every variable is positively biased. Or in other words, every variable has the property that it occurs at least as often positively as negatively. Okay, and now I'm going to consider the assignment to this instance, which assigns every variable to 1 with probability 2/3 and 0 with probability 1/3. Okay, so what's the expected value of this assignment? So for instance, take a constraint in which both literals are positive. The probability that such a constraint will be satisfied by this assignment is the 2/3 that the first variable is assigned 1 times the 2/3 that the variable, the probability that, sorry, 2/3 that the probability of the first variable is assigned 1, 2/3 is the probability the second variable is assigned 1, and this is independent, so it's 4/9. Similarly, if there's 1 positive and 1 negative, it's 2/9, and if they're both negative, it's 1/9. Okay. And I can do a sort of similar trick as I did on the previous slide. So now this was the inequality that we had before, except that now it's actually an equality because every variable is positively biased. So I have this. I can multiply both sides by 2/9, and I get this equation. And then I can compare this. And again, we have something which is non-negative, which is extra here. So this thing is at least this thing. Okay. And yeah, so the original analysis did something more complicated. It used a probabilistic assignment, but didn't always use 2/3. And it turns out, and we don't completely know like a convincing enough reason why, but 2/3 works here. And in fact, if you do the same analysis for k and for any k, it is always true that there's just some number that when you pick that number, then the analysis sort of works out optimally. And it would be nice to have a good understanding of why that's true. Okay, so the recap here overall is that what we have done, we've taken a max 2and instance and we've related the value of the best possible assignment to some quantity, which we called its biasness, which basically says something about how often, for a typical, you can think of this as like for a typical variable, does it usually occur positively or usually occur negatively, or is it sort of a mix between the two? And once we wrote down the inequalities, the actual analysis was basically looking at two inequalities, then being like, oh, well, there's like a non-negative thing on the right-hand side of one, so it's at least the left-hand side of the other, or something like that. And one thing which is very useful for us going forward is that the way that we proved the lower bound, which was on the previous slide, was actually by giving an algorithm, which you can think of as like a self-contained classical algorithm for the max 2n problem. So you just take an instance, and instead of flipping the negatively biased variables, you could just think of it as assigning negatively biased variables in like the negated way. So here's like a classical 4/9 approximation for the max 2n problem. You take your instance, you look at every positively biased variable, and you assign it to 1 with probability 2/3 and 0 with probability 1/3. And then you take every negatively biased variable and assign it to 1 with probability 1/3 and 0 with probability 2/3. And this analysis implies that that is a 4/9 approximation. Okay, and the upper bound, you had to flip variables according to what an optimal assignment is. So this doesn't necessarily give like a classical sort of algorithm or anything. Yeah, and I want to reiterate that when we actually implemented this as a streaming algorithm, we required that you could estimate the norm, L1 norm of a vector as a black box. And that was why this sort of natural classical algorithm was implementable as a streaming algorithm. And when we're interested in beating 4/9 using sort of additional space, we no longer have the luxury of being able to rely on sort of these sketching results for norms, and we need to sort of implement something ourselves. Okay, so now I'm going to tell you in the remaining time some about how you can sort of generalize the analysis that I was saying before to beat 4/9 using a sort of slightly more amount of space. Sorry. Yeah.
So I guess, more generally, maybe you could look into the max 2n and like you get some number of points for the fraction of constraints where the number of specified literals is 2, a fraction of points,
Yes.
number of points where it's 1,
Yes.
0. So like, does this similar analysis give you the right answer for any like valued CSP like that?
I'm not
Does it
sure.
rely on it being like monotone, like you get 1 point for Hamming weight 2 and 0 points for the other two Hamming weights, or?
Okay, so this is, I think my general impression is that I have sort of no idea why this analysis works in like a convincing way. So I think, so in this, one of the papers that we had, we showed that some similar thing happens, not just for 2and, but for k and for some other symmetric CSP monotone or some threshold functions and different things like that. That this similar phenomenon where, I guess, I don't know if this is exactly what you're saying, but basically you take your instance and then you just look at how many, you just assign variables based on the sign of their bias to some fixed constant, to 1 with some fixed constant probability and 0 with the remaining probability independently. And those type of algorithms for some class of CSPs are at least in this square root n space sort of setting.
Can you remind me of the
Yeah.
upper bound? You have upper bound for 4/9, so it's been like.
Yes, yeah, this is,
over down.
yes. So this is not, yeah, so this is not from our work. This is from work from a few years ago, but I think, yeah, so this algorithm is optimal in square root n space. And we know that similar algorithms are optimal in square root n space for a pretty big class of symmetric functions. But I don't know, like, so I know that they are optimal because we have the upper bound and the lower bound, but I think it would be nice to have a convincing explanation of why something that's this simple is optimal. Yeah. Okay. So now, sorry for the bait and switch. I'm going to go back to talking about die cut instead of 2and, because it was useful to think of 2and before, and it's useful to think about die cut now. Okay. So in a directed graph, you can define a quantity called the bias of a variable, a bias of a vertex. Sorry, this is what's annoying about going back and forth between these two things. Now I'm going to think about the bias of a vertex, which is the difference between the out degree and in degree over the sum. Okay, so the out degree is analogous to the positive weight that I was talking about before, and the in degree is analogous to the negative weight that I was talking about before. So this bias number is between -1 and 1, and you can think of it as, okay, let's say I have a vertex whose bias is close to 1. Then what that means is that almost all of the edges are outgoing. If I have a variable whose bias is close to -1, that means almost all of its edges are incoming. And if I have a variable whose bias is close to 0, it means it's a mix between sort of outgoing and incoming edges. And the hope is sort of a little bit similar to what we did before. You know, a variable that looks, vertex that looks like this, maybe you should put it like this. Basically, we know how to assign it because almost all of its edges are sort of incoming. And these variables are maybe harder to assign, vertices are harder to assign because there's a mix of incoming and outgoing edges. Okay, so thinking about the bias of a vertex in this way, the previous analysis showed that if what we want to do is just take every vertex and then assign it sort of probabilistically solely based on the sign of its bias, you get a 4/9 approximation. Okay, and a caveat is, again, I guess this is this assign every variable based on the sign of its bias is like a classical algorithm. But when we want to implement it as a streaming algorithm, we don't have the space to do that. So we have to do this other trick where we use something else as a proxy for the value of that assignment and sort of sketch it in some way. And we're no longer going to be able to do that. But for a second, I want to forget about streaming and just think about classical algorithms. So we have this classical algorithm, which is like a 4/9 approximation. So the way that algorithm worked was you probabilistically assign every vertex solely based on the sign of its bias. So there's this paper of Feiga and Joseph where they study a slightly more general class of algorithms that also assigns variables based on the magnitude of its bias. So this might make sense because, this 4/9 approximation that I was saying, it treats a vertex whose bias is like 99% and whose bias is 1% the same because they're both positive. But maybe you want to be more aggressive on vertices whose biases are like very close to 1 and things like that. And that's sort of what the intuition behind this class of algorithms would be. So formally, such an algorithm would be defined by a partition of the space of possible biases between -1 and 1. And then for each of these intervals, I'm just going to pick some probability with which to assign vertices which have a bias in that interval to 1. And given sort of this data, I can define a so-called oblivious algorithm. And it's oblivious because it ignores everything about each vertex aside from its bias. And I'm just going to look at all the vertices which are in what I'll call bias class A, which is just in some interval in this partition. And then I assign vertices to 1 with some probability, which is sort of the same probability for all the vertices in that class, and 0 with the remaining probability. So so you can think of the 4/9 approximation that I talked about before as one of these algorithms with only 2 classes, because it only cares about whether the sign of the bias is positive or negative. But even using 3 classes where you're willing to treat variables whose bias is close to 0 differently than the other 2, you can do better than 4/9. And what Feiga and Joseph showed in 2015 was that there's some partition, although it uses like 100 intervals or something like that, and some assignment of each interval to a probability where you get like a 0.483 approximation. And they also proved a lower bound that you can't do better than 0.49. Excuse me. And the way they did this was they come up with this function in some way, and then you can characterize the worst case instance for such an algorithm using a linear program. So they just write down some big linear program and solve it, and then say like the value of this LP is 0.483, and therefore this algorithm gets at least a 0.483 approximation. Yeah.
Is there something magic about 100, or could they have also done?
No. It's not magic about 100. And I think I think the magic thing is that the function looks somewhat like this, and the LP gets like it would be another thing which would be terrific would be getting an actual understanding of what the optimal function is, as opposed to I played around with this on the computer to some extent. It appears to look something like this, like a sigmoid or something, and gets better and better as you add more and more classes. But of course, the LP gets bigger and bigger. I think it grows quadratically or something. So I think they only went up to 100. Yeah.
I mean, that looks very suggestively like this piecewise.
Yes, but you may be able to actually do better by like going up. I really don't know. And like the thing is that whenever you have sort of a candidate, you have to then solve this big LP that tells you how good it is. So I think I would be very excited about having some like analytic understanding of actually I think I do have an analytic understanding of why this does better than 4/9, but I don't know what the sort of best possible shape is. But regardless of what it is, we know it can't do as well as 0.49, so it can't get all the way to 1/2, which is what we would really want. Yeah.
Why are you even like partitioning and needing a like finite number of classes instead of just making this some continuous function from the bias?
Yes, so this is a good question. So I think there's two reasons. One is that when you do an LP, like the LP basically has a bunch of variables, which are like the number of edges from bias A to bias B. So if you want a finite number of variables, you need like basically a finite sort of number of possible biases. And the secondly is that when we do this with a streaming algorithm, we also need that property that there's only sort of like a finite number of possible biases.
Oh, you do? Okay.
Yeah.
So it's not just, okay.
Yeah. Yes, but you're right. I mean, you could think of some arbitrary function here, and then you could think of a classical algorithm which assigned based on the bias. And in fact, that's like the true thing that you would actually want to understand. But what you can't understand like on a computer, like with an LP, for example, is this sort of thing. Okay. So like, what does this have to do with streaming algorithms? So for a graph and some fixed partition of the space of possible biases, we define a matrix, which is we call the snapshot of a graph. And what this matrix is it just counts the number of edges in the graph that go from class A to class B for each pair of possible classes. So this is a matrix, and it's entries are non-negative and sum to 1. And the reason why this matrix is so useful is that the expected value of the assignment, which is produced by an Oblivious algorithm, is just a linear the entries of this matrix. Because what's the probability that any particular edge is satisfied by this assignment? It's the probability that its left endpoint is assigned correctly, which is some number which depends only on its bias, and the probability that its right endpoint is assigned correctly, which also depends only on its bias. So overall, the value of this assignment only depends on the number of edges which go from bias A to bias B for each possible pair of these sort of classes of biases. And this is convenient because it means that given an estimate for this matrix, we can estimate the value of the assignment that the Oblivious algorithm would produce. And this matrix, we think of as a constant size matrix, which is why it's useful to have only a constant number of different classes. So the expected value of this assignment, again, we know is like an underestimate for the value, but not by factor more than alpha. So if you have an estimate for this snapshot matrix here, you can estimate this expression, which gives you like an alpha minus epsilon approximation to the value of the assignment. So overall, the sort of moral here is that we can forget about Oblivious algorithms, and getting a better than 4/9 approximation reduces really to a streaming estimation problem, which is, you see a graph that's streaming past you and you want to estimate these snapshots. And if you can get, arbitrarily good estimates like an L1 norm, then you're happy and you can beat 4/9. And that's sort of what is going on sort of for the remainder of the talk. Okay. Yeah. So the first sort of special case that I want to talk about is that we can get these estimates of the snapshot in very small space, logarithmic space, under an additional assumption. And this additional assumption is that the edges which are showing up in the stream are randomly ordered instead of adversarially ordered. And sort of for the record, this was an interesting thing because we know max cut and some other very hard CSPs like remain hard even under this sort of random ordering assumption. And the reason that this random ordering assumption is helpful and lets us get like a very simple log space algorithm is that it lets us do the following: sample a small number of random edges and then look at the biases of their endpoints. So again, this is now, in other words, this is a classical algorithm, which is simple. And that's, this random ordering assumption lets us implement it as a streaming algorithm. So if you want to think about this as a classical algorithm, basically we have a graph, we sample some subset of its edges, and then we look at the endpoints of all the edges that I sampled. And this set of edges is small, it's like logarithmically sized. Okay. Then I just look at the biases of all these vertices, and then I estimate the snapshot just looking at how many, among the edges that I sampled, how many edges are going from bias A to bias B. And I get some estimate of the snapshot purely based on this information. So does that make sense as like a plan? So the goal is to try to, I guess maybe I can reiterate. So the goal is to, essentially estimate the total number of edges in this graph that go from bias A to bias B. And what I'm saying is just sample a random subset of edges and then look at how many of those go from bias A to bias B. So this is just some like sort of simple sampling type procedure. Okay. So the reason that the random ordering assumption lets us do this is just if I look at the initial chunk of edges which come in the stream, since the edges are randomly ordered, that means that the first edges that show up in the stream are a random sample of all the edges. Okay, this is the only reason why the random ordering assumption is convenient. You could also think of it as like a streaming algorithm with the additional property that you get to see a random sample of edges at the beginning of the stream. So if I want to make an algorithm, I just take my randomly ordered stream, I look at the first edges which show up, I look at the endpoints of those edges, and then over the remainder of the stream, I just store the in degree and out degree of all the vertices that appeared in the beginning of the stream. And I don't need to know anything else about the graph structure or anything in the sort of, I mean, this chunk is like, n minus log n edges or something. It's like the vast majority of the stream. I don't need anything about it except how it affects the in degree and out degree of the vertices in the beginning of the stream. And then after the stream is over, I have this set of edges and the set of vertices. I can calculate the bias of all those vertices, and I can look at the fraction of edges which go from bias A to bias B among the edges that I sampled. Okay, so this is just how to implement this sampling procedure as a streaming algorithm under this random ordering assumption. Okay. So a slightly more complicated variant of this takes place when, instead of assuming that the graph is occurring randomly ordered, I assume that every vertex in the graph has bounded degree by some constant. Or in other words, every vertex is only touched by a constant number of edges. Okay. The reason, maybe again, there's a classical algorithm that we really want to implement as a streaming algorithm. And the classical algorithm here is to sample roughly square root n random vertices, and then store the induced subgraph on the vertices and look at the biases of those vertices. So just as a classical fact, if you have a graph with a sparse graph, then you want to sample a random subset of the vertices and look at the induced subgraph. In order for the induced subgraph to even have any edges in it in expectation, you need to be sampling order square root n vertices as like a birthday paradox type thing. So that's exactly where the square root n space sort of usage comes in. Okay, so I can sort of also present this algorithm, but it's going to need some simplifying assumptions like that we know the number of edges and that there are no isolated vertices in the graph. These are both sort of convenient. I think I can say why they're convenient. But again, the sort of informal picture of the classical algorithm that you would try to implement as a streaming algorithm here is that you start with some graph. You now, instead of sampling edges, you sample vertices. So I sample some subset of square root n vertices. And then I look at the induced subgraph on these vertices. And then I estimate sort of how many edges go from bias A to bias B in the overall graph just by looking at this induced subgraph. Okay, so these are sort of two classical algorithms, one based on sampling edges and one based on sampling vertices that you could want to implement as streaming algorithms. Okay. So again, the algorithm for the bounded degree case looks something like the following. Before the stream, you sample some square root n space subset of the vertices. During the stream, you store all the edges whose endpoints are both in the subset of vertices that you sampled. And then everything else is the same as the random ordering case. Over the stream, you track the in degree and out degree of all the vertices that you sampled. And then at the end of the stream, you calculate all their biases and use that to estimate this snapshot matrix. Okay. So let's think a little bit about the correctness of this algorithm. So the goal is basically to show that the number of edges going from bias A to bias B in the sample is roughly the same as the number of edges going from bias A to bias B in the overall graph. So yeah, let me think. I I mean, basically, I guess I said X was the number of edges that you sampled going from bias A to bias B, and T was the number of the true global number of edges going from bias A to bias B. And you're trying to show that, you get this correct estimate. So you can think of the number of sampled edges which are showing up from bias A to bias B as a sum of indicators of each of the different edges that go from bias A to bias B in the original graph. So this is just some random variable, which is like a sum of indicators. And the random ordering setting, remember, the set of edges which we sampled was like a uniformly random set of edges. So this, these, which edges are showing up are like uniform and independent. And this means that you can just use like a normal Chernoff bound to show that the number of edges which are showing up from bias A to bias B in your uniform sample is representative of the number of edges going from bias A to bias B in the global graph. What's slightly more complicated, and the reason why we have to actually use a bounded degree assumption, is that in the bounded degree algorithm, remember, instead of sampling random edges, you sample random vertices and then look at the induced subgraph on those edges. And now we no longer have this independence property, because in particular, let's say I have two edges in the graph which share one endpoint. That's sort of like the tricky case to think about. Then it's, there's only three events that determine whether these two edges will jointly show up in the graph: that their shared endpoint is sampled, and then that each of their individual endpoints is sampled. So these two events, that this edge shows up and that this edge shows up, are no longer independent. And what this means is that in order to make the correctness work out, you need to rely on the fact that this is a bounded degree graph, which means that each edge cannot share endpoints with that many other edges, which means that each edge, whether it shows up in the induced subgraph, is independent of all but like a constant number of the other edges which might show up in the induced subgraph. Okay, and so yeah, you can work out with like I don't know, we use Chebyshev. You can work out some sort of bounded independence thing, like it's independent of all but a constant number of the other variables. And what that means is roughly you need like a square root D factor that shows up in the number of vertices that you sample. So that's why there's this extra square root D factor showing up in the space usage. So I guess that was, I don't know where that was. Yeah, oh, sorry, it's all the way back here. Yeah, so the space usage degrades as the degree of these graphs gets bigger and bigger. You need to store more and more vertices as the degree of the graphs gets bigger and bigger. And it shows up because, yeah, when you actually calculate the variance of this estimate, there's like a square root D term in it. Yeah, okay, anyhow. So I guess the thing that I want to conclude by talking about is what happens when we no longer have this bounded degree assumption. And this somehow turns out to make the problem much more annoying. And a metaphor for why this is true is, let's say I wanted to estimate the L1 norm of a vector. Okay, so this is like the sort of thing that I wanted to do in the original 4/9 approximation that I was talking about. I want to estimate the L1 norm of a vector. So under like a bounded degree assumption, which in this setting would be that each coordinate of the vector is touched only a constant number of times during the updates, this problem becomes very easy, because it's equivalent to estimating an average of a list of n numbers where each number is between 0 and a constant. Okay, so all you need to do is like sample a constant, big enough constant number of numbers from this list and then take the average. And how big that constant is depends on the upper limit of what these numbers can be. So yeah, I mean, they had to do more work to get a sketching algorithm that worked for norm estimation without a bounded degree assumption. And similarly, we have to do a lot more work to get an algorithm for this snapshot estimation problem without a bounded degree assumption. Yeah, so let's see. Yeah, so the very general outline of how this algorithm works that actually gets the square root n approximation without any bounded degree assumption is that we break the graph into a bunch of layers, and each layer sort of corresponds to the vertices whose degree is roughly, say, 2 to the I. So, there's log number of different layers. And then we aim actually for a more sort of specific thing. We aim to calculate how many edges in the graph go from bias A to bias B and layer I to layer J. And this is some more granular information. So the question is, how can I sample vertices with degree roughly 2 to the I? And to do this, you can do, like, the trick that we use is to do some sparsification. So you take the graph and then you sparsify it so that high degree vertices now have low degree. And then you can look at which vertices have low degree in the sparse graph. Something like sort of, there's like some back and forth there. But this causes some additional problems, which is that you no longer exactly know the in degree and out degree of vertices in the global graph. You only have estimates. And this somehow wreaks havoc on when you want to actually estimate sort of how well the algorithm will do. So yeah, just to show you like a picture of what happens, let me think. Okay, yeah, just to show you like a picture of what happens, you could think of this as like a generic sort of classical problem, which is not related to the estimation stuff I was talking about at all. So you can think of this basically as, say there's some matrix, then I don't know the matrix, but an adversary gets to take that matrix and then redistribute each of the entries over neighboring entries of the matrix. And I only get to see this matrix after this redistribution has taken place. Can I say anything about what the original matrix looks like? So it turns out you can't, because, like, you know, I don't know. I mean, you could go from this matrix with a 1 here and the 1 that's redistributed over all these neighboring entries. And yeah, you have no hope of saying anything exact about what the original matrix looks like. And so what happens in the paper is, instead of asking to estimate the specific entries of a matrix, we ask to estimate averages of entries of the matrix over windows. And sort of pictorially, why this is convenient is you get some phenomenon, like, let's say you're trying to estimate the average of all the entries in like this green square. Even if some entries could shift by 1, you know, entries which are sort of close enough here will always contribute. Even if they shift sort of by 1 going out, then they'll still count. And sort of edges which entries which are outside, far enough outside, will also never contribute. And somehow, like, altogether, this lets you estimate sort of a smoothed version of the snapshot, where instead of looking to actually estimate the snapshot, you look to estimate entry averages over sort of regions of the snapshot. And you have to lose some additional factors which you can control from doing the sort of smoothed analysis. And that's what you can actually estimate using a sort of square root n space algorithm. And yeah, so altogether, you know, we know based on this how to get a square root n space algorithm, square root n polylog n, which gets a 0.483 approximation by implementing this Oblivious algorithm as a streaming algorithm. And yeah, Oblivious algorithms are sort of known not to be good enough to get a 0.5 approximation. So like, one general sort of very interesting question that I'm interested in is, yeah, can you do better in square root n space? Could you prove a square root n space lower bound? You know, you could imagine that as you use more and more space up to a linear amount of space, you can get closer and closer to 1/2. That would be like a very cool result. I don't know. So yeah, so I guess that's sort of the space that's left open by the current result. It's like a whatever 0.5 minus 0.483 is, and whatever n over square root n is. Yeah, anyhow, yeah, that's the talk. Yeah, any questions?
The reason why it's like, you should look at is this, I forget what it was, like, in degree minus out degree over in degree plus out degree. Well, you might just say, like, I'm going to characterize the vertex by like the number of times it appears positively minus negatively on the left, and how many times it occurs on the right. Not characterized by 2 numbers. And you could study like rounding functions f that were from, you know, the plane into, the picture you have with like pi is like a 1-dimensional picture. You could have a 2-dimensional rounding function there.
Yes.
I mean, could this be better, or?
So let me think. I mean, so one thing, okay, so one thing which we thought briefly about is, you know, this is like a normalized thing, but you could think, you know, I take the in degree minus out degree over in degree plus out degree, but instead, like, this is sort of a, you know, the more granular information is just the in degree and out degree of each vertex. But I think if you have an instance,
Oh, sorry, yeah, it's not, there's not positive thing. Yeah, so just.
Yeah.
Integrate and not degree.
yeah, but I think if you have a graph, so I think somehow the fact that we're considering a one-dimensional thing reflects that if I have an instance of if I have like a graph that has a certain die cut value, I could also take any particular edge and blow it up, any particular vertex and blow it up into many copies that are identical and are disconnected. And then those, yeah, so like somehow you lose a coordinate from having to, from being able to do that. So if I take a graph that has a certain die cut value and I take a particular vertex that say has high degree, I could blow it up into many low degree copies that are isolated from each other while preserving the die cut value. And so that means you actually don't have sort of a degree of freedom for the total degree of any vertex. The only thing that matters is the sort of difference between the in degree and out degree relative to the total degree of a vertex, if that makes sense. Yeah. I think you like provably can't do better by considering both the in degree and out degree as opposed to just their sort of normalized difference. Yeah.
So is it correct that the LP integrality gap for die cut is half? You know?
Yes, it is. Yeah.
Like a half versus a quarter?
Yeah. So I think that's like another, one thing which I'm sort of generally interested in is just understanding what it is about die cut that means you can do better than the trivial thing, whereas for max cut you can't. And somehow, it's really related to that. This bias quantity only makes sense when you think about the fact that the constraints are not symmetric. So if the constraints are somehow symmetric, then you, so there's, actually predicates which support a one-wise independent distribution of satisfying assignments are like provably like approximation resistant in very strong senses. So only ones which have sort of some notion of sort of asymmetry, you could hope to do better. But yeah, it would be very nice to get sort of more, I don't know, I think a lot of these results somehow end up looking like we know that you can do better. But getting very convincing understandings for like why you can do better in certain cases and not better in other cases, I think would be very nice. Yeah. Any other questions? Okay.